Good morning, everyone. Welcome to the class of C333 Environmental Engineering 2. So, in our last class, we discussed this design example of a sewage treatment uh, plant. That's basically a sewage stabilization pond. Sewage stabilization pond. We saw the design of a facultative and maturation pond. Okay. So now the second problem they're telling repeat problem one, the same problem. Now incorporating anaerobic pretreatment. So here in this problem, we had the facultative pond as well as we designed two maturation ponds, right?
Yes,
Right,
sir.
guys? So
Yes,
now
sir.
they're telling, okay, now design the same, but now incorporating one anaerobic pond for pre-treatment at the beginning. So you do this anaerobic pond. For anaerobic pond, our D is a bit higher than the facultative and maturation pond. As you can see, these are 1.5, 1.5. In this case, we will take this 3 meter approximately. And anaerobic pond maximum detention time can be 5 days. Otherwise, it will be facultative pond. Okay, so this is 5 days. And let's say efficiency of this anaerobic pond is 70%. So we are assuming these values. Then the surface area of the anaerobic pond will be, we know that A equals to Q into T over T. So you just put the value of Q. Q is given, by the way. Q is given, which is 10,000 here. T is 5 days and D is 3 meter. We got A equals to this. Okay. Now we know that efficiency of a pond is what? Is Li minus Le divided by Le into 100%. So you can write Le equals Li minus Le into 100%. Okay.
Yes, sir.
Now, um, or if you want to calculate Le, then you can also write Li equals to, from here, equals to Li by Le minus 1. Let's do this. So from here you can write Le equals to E by 100 minus 1 into Li. So Le equals to Li into E minus 1 minus E. I'm sorry, it will be 1 minus E. 1 minus E by 100. Okay. So LE will be Li by Le minus 1. We do this again. Le equals to Le minus by Li minus 1 divided by 100. Okay. So Le by Li equals to uh, 7. From here you can write this actually. Le equals to Li into 1 minus E by 100. Okay. Now E equals to what? 70. So zero point 0.7. 1 minus zero point 0.7. What is Li, guys? Li was given. This is 630 milligram per liter. Are you following me?
Yes,
Yes,
sir.
Yes,
sir.
sir. Yes, sir.
So you can write this 630. Now 630 is entering here. What is getting out from here, guys? Li. Li was 630. What is Le? 189. So this is 189. Now you tell me for this facultative bond, what is the value of Li? Influent VOD concentration. Guys,
630. Yes, sir.
for this facultative bond, what is the value of Li? Influent VOD concentration.
630.
Okay, 630. Anyone else? Anyone else?
630 होता.
630. Anyone else?
So 189,
180?
9.
189. So this is the flow. I already told you this is 189. How it would be 630 here? 630 has already been treated by anaerobic pond. So no way it will be 630 again. This is the flow, 189. So the in effluent concentration of anaerobic treatment plant 189 should be the influent concentration of facultative pond 189. Am I right?
Yes, sir.
Yes, sir.
Are you getting this? Why 630 will be here? 630 has already been treated by anaerobic pond. Are you following me?
Yes, sir.
Yes, sir.
Yes, sir.
630 has always been treated. So why would it be like this? Okay. Well, here this will be Li. Okay. That was a mistake. It will be Li minus Le divided by Li. Okay. Li minus Le divided by Li. This is Li. Okay, that makes it 1 minus Li. Okay, and then you will get Le equals to Li into 1 minus E by 100. So that's the equation we got. We used it here. Okay. So anyway, what I was telling here is this 189 flow here will be the influent flow of facultative pond Li 189. So here let's assume D equals to 1.5, Le equals to 60 milligram per liter. Similar to the previous case, we assumed Le equals to 60 milligram per liter, D equals to 1.2 meter. So we can calculate our area, surface area, using this formula, right? Where Li is what, guys? Li is what? Huh? Here Li will be what? For the facultative bond, Li will be
One.
189. So this will be 189. Then Le, I have assumed it is 60. Le is 60. D equals to 1.5 meter. And this is K, right? K is given. K is given, which is zero point 0.3 per day at 20 degrees Celsius. But remember, if the temperature is other than 20 degrees Celsius, then you have to convert this value to that temperature, particular temperature. Okay, from here we know all the values. You know Q equals to 10,000. So finally you get this. Okay.
Yes, sir.
Now you see this is 47,000. Previously this was 264,000. So this has been reduced much. Why? Because a big portion of the BOD has been treated in the anaerobic treat pond. So the influent load here was 189 for facultative pond. But previously here it was 630. That's why this was higher. Clear?
Yes, sir.
So your time detention period T will be calculated from this equation. T equals to A into D over Q. T equals to A. This is A. This is D. And this is Q. Clear? Which is 7.2 days. Any question?
No, sir.
And then in the for the maturation pond, same, let's D equals to 1.5 meter, T equals to 5 days, and number of ponds equals to 2. So you calculate LE and NE. What is the formula? Same, this is the formula. This is the formula. So when you will be applying this formula, then you will take this pond, and this pond. So how many? 1, 2, 3, right?
Yes, sir.
Look at this. 2 plus 1, that's 3. Okay. Okay.
Yes, sir.
Now if you consider these 3, 1, 2, and 3, then what is your Li? What is your Li?
So 189.
189. Remember this. Your Li is not 680. No, 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 no. Your Li is 189 because you are considering this. So your Li is this 189. So look at this. This is 189. Okay,
जी
जी
सर.
sir.
which is less than 25 milligram per liter, which is the standard value given here. So BOD loading is okay. Now for the fecal coliform, total coliform, for the total coliform, fecal coliform, we are dealing from here. Why? Because the coliform starts dying or starts being killed from here. So we will take this 1, 2, 3, 4. How many guys?
4.
4.
1, 2, 3, 4. We're taking this system. So what is the Li now?
630 plus 189.
30. 631 for BOD, right? And what is your Ni? Initial vehicle coliform. Where? 4 into 10 to the power 7. Did you see? Initial. You have to put this here. Did I make it clear?
जी sir.
How many? 1, 2, 3, 4. Look at this. 1, 2 plus 2, 4. 1, 1 and 2, 4. 2, 3, 4. Clear?
जी sir.
And this is 1 plus k into t for anaerobic. This is for anaerobic bond. This is for facultative bond. And this is for uh, this one is for anaerobic bond. This one is for facultative bond. And this one is for what? This one is for what? Hello? This one is for anaerobic bond. This one is for the middle one is for the facultative bond. Okay? And these two is for what?
The maturation pond.
Maturation
Mat-
pond.
Submaturation.
how many maturation points? Two. 1, 2. So this is a square. Okay. What
Yes
is
sir.
the retention time in anaerobic pond? 5 days. So you have written 5 here. You have written 5 here. What is the retention time in facultative pond? 7.2 days. So you have written 7.2 days here. What is the retention time in maturation pond? 5 days. So you have written 5 here. There. And these are the
Yes sir.
values of KB, KB, and KB. That's it. Which is less than the 5,000, even the standard value. So it is good. Done. Okay. Any question, guys? Any question?
No, sir.
No, sir.
Okay. Just to make it uh, clear again, here in this case, we have used 3 ponds. This is three. One, two, three. These 3 ponds. That's why our Li is 189. We could also have used these 4 ponds here. In that case, we had to return another part for anaerobic pond. And our Li would be what? Our Li would be, in that case, our Li would be what?
স্যার কোন পয়েন্টের জন্য বললেন?
If I had taken 4 ponds here, in this case, then what would be our Li here?
স্যার তখন 630 প্লাস 189 হবে না স্যার?
189. Why? Because 189 is a later stage. If you take this system, just think simply. If this is the system, what is your Li?
630.
630.
630. It's not simple. How much is going? 630. Now what is happening? This has been reducing at different stages. That's a different thing. But for this system, what is entering? 630. That's it. So Li will be 630. Clear?
Yes, sir.
Yes, sir.
Okay, in this problem, they're telling what? Design a stabilization pond system to treat 1000 meter cube per day of domestic sewage, which has a BOD of 500 milligram per liter and fecal coliform count of this to meet the WHO standard for unrestricted irrigation. The effluent will also meet the Royal Commission standard of 20 milligram per liter for BOD. Okay, fine. So 500 has to be reduced to 20, and fecal coliform has to be 4 into 20 by 7. That has to be reduced to less than 100. The design temperature is 17 degrees Celsius. Okay. So this is kind of similar thing. So in this case, look at this. This values bacterial reduction rate constant and BOD reduction rate constant K has been given at 20 degrees Celsius. But the system, the temperature at the stabilization pond is what? 17 degrees Celsius. So you have to convert these values at 20 degrees Celsius to 17 degrees Celsius. Clear?
Yes, sir.
জি স্যার।
What is the formula? Formula is KT equals to K20 into theta to the power T minus 20. So in case of KB at 17 degrees Celsius will be KB at 20 degrees Celsius. What is that value? KB at 20 is 2.6. So 2.6. What is the value of theta? Theta value is given, for example, 1.19. Theta value is 1.19. To the power, what is the value of T, guys? 17. So T equals to 17 here. Minus 20. Clear?
Yes, sir.
Okay, so you got the value of Kb at 17 degrees Celsius. Similarly, you need to calculate the value of K at 17 degree Celsius, which is 0.718. Done. So for the facultative pond, let's say d equals to 1.5 meter, t equal to 36 days. Okay, so what will be the volume? The volume equals to what? Q into T. Am I right?
Sir,
Volume equals to Q into T. Yes, go ahead.
স্যার টি ইকুয়াল 36 ডে এটা কি স্যার মানে দেওয়া
Assuming.
থাকবে?
We are assuming. We are assuming.
ঠিক
In
আছে।
facultative pond, usually this can be 30 days, 7 days, 15 days. So you can assume any value. Okay, you do not know the value initially, right? So you can assume it. You can assume 15 days, 7
ওকে
days,
স্যার।
and you'll see, check it. Okay, this is not going to happen. So to make this, then you need to increase your T, or you can follow this method. First of all, you assume LE instead of T. Assuming T, you are assuming LE. Okay, and then you calculated A, and from there finally you checked whether it is allowable or not. Okay, so finally you calculated T. This is one method. Another method is, instead of calculating T, instead of assuming LE, you assume T. Clear?
ইয়েস স্যার, ঠিক
That
আছে।
which is we are doing here, assuming T here. So volume equals to Q into T. Okay. So Q equals to what? Q equals to 1000 meter cube. So 1000, and what is T? T equals to 36 days. So your area is what? Area equals to what? Area equals to volume by what? Depth. So area equals to volume, which is 36,000. We got it from here, divided by depth. What is the depth we assumed? 1.5 meters. So 1.5. 24,000 meters square. Now you need to check whether your lambda s is less than lambda is allowable. So what is the equation of lambda s, guys? What is the equation of lambda s? Remember, lambda s equals to 10 into Li into Q over A, kg per hectare per day. Li Q A. So you put the value here. Lambda s equals to 10 into Li Q divided by area. This is 10. Li is what? 500. 500. Are you following me?
ইয়েস
Yes,
Yes,
স্যার।
sir.
sir.
Yes.
Q is what, guys? 1000. A is what, guys? You have calculated this 24,000. So you got lambda s kg per hectare per day. Now we calculate lambda is allowable, which is 20t minus 120, right? This is the formula, 20t minus 120. So T is what? In degrees Celsius temperature, which is in our case 17 degrees Celsius. So you put 17 here. Okay. This is not plus, this is minus. So you'll get 220. Now compare this value. Now compare this value with this value. This is your allowable limit. So this has to be smaller than this. So this is smaller than this. So fine. Okay. For the maturation pond, uh, assume we are using two maturation ponds. Depth is 1.5 meter and t equals to 7 days. When you are assuming, guys, you have to remember that we have some ranges. of depth for each of the pond. Let's, for example, let's say for facultative pond, uh, D should be in this range, clear, and LE should be in this range. So when you are assuming LE, you should assume something in between this. You cannot assume 200. Did I make it clear? Similarly, when you are assuming D, you cannot assume 3 meter. No. For facultative pond, you have to assume in this range. Clear?
Yes, sir.
For the anaerobic pond, D can be 3 meter. For the anaerobic pond, T should not be more than 5 days. Okay, and D can be approximately 5 meter. Okay, for the facultative, I already told you these values for facultative. This is for facultative, and for the maturation pond, your D should be in this range depth, and your T should be in this range. Sometimes maturation pond detention time can be 5 days or less also. Okay, so based on that, we are assuming. Look, for maturation pond, we are assuming T equals to 7 days. We could have also assumed 6, 5, or 4, but we cannot assume 10 here. Okay, D equals to 1.5 meter. So your area will be what? Area equals to, I told you, Q into T over D. Area equals to Q into T over D. So you got this. Now the formula here, LE, this is the formula. You use this. How many ponds you have, guys, here? You have one facultative pond and two maturation ponds. Am I right? Are you following me?
Yes, sir.
Yes, sir.
One, two, three. So two maturation ponds, one, two, and one facultative pond. So two maturation ponds and one facultative pond. This is the value of K, which you have determined here. This is the T for facultative pond, which is 36 days. You have assumed it, and your T for maturation pond is 7 days. We have assumed it here. And for this system, what is the LI, guys? For this system, LI is 500. No anaerobic pond, so this is 500. Clear? Is it
Yes,
clear?
sir.
Yes, sir.
So you got this 13.37. Now you check this value with the given 20. Is this less than 20? Okay, then it's fine. Now if this was greater than 20, then what you could do, you could have increased the depth. No, not depth. You could have increased the number of ponds. Instead of 2, you could have used 3. Okay, or you could have increased the tea a little bit one day, maybe 8 days, and check. You cannot go far beyond 7. Okay, 8 day or 9 days. Okay, or you could have incorporated an anaerobic pond at the beginning, or you could have increased the surface area of the facultative pond. There are many options. And finally, you do the NE, which is same as LE. You just put the value of NI here. NI is what? 4 into 10 to the power 7. Do you see this is not okay, guys, by the way? This is 510. And this is what? It has to be less than 100. Is it okay? It's not okay. Right?
जी sir.
So what they are using n equals to 4. In your case, you should not go suddenly to 4 from 2. First, you should increase 1, 3, and then you should go 3, 2, 1, 4. Okay? From 2 to 3 and then 3 to 4. If you are experienced, then you could use directly. But now, for your case, since you new in this area, so you should increase one by one. And you calculate LE and NE again. How many ponds you have? Maturation. Then you have maturation and then another maturation. So how many? 1, 2, 3, 4. So this is 4. Clear?
Yes sir.
Okay.
স্যার স্যার আমরা ফ্যাকাল্টেটিভের ক্ষেত্রে কি স্যার টিটা অ্যাজিউম করলাম কি হবে 36
I cannot hear you. You need to speak loud. Can you please speak loud?
স্যার ফ্যাকাল্টেটিভের ক্ষেত্রে আমরা 36 কিভাবে অ্যাজিউম করলাম সেটার কি কোনো রেঞ্জ আছে
Facultative, we have assumed what?
36
36 days.
এটা
T.
কি জি
Yeah. In case of a facultative bond, your T can be 32 days, 36 days, no problem. Clear? In this case, your T can be 36, 32 days, no problem. Uh, this is our facultative bond, right? Here, somewhere it might be written. Let's check.
স্যার রেঞ্জ দেওয়া নাই স্যার আমি চেক করেছি
Okay, they didn't write it explicitly, right? So this is common in case of facultative bond, T 1 month or 1.5 months. This is common. You can use it. Clear?
স্যার
Fine. Okay. Any other question, guys?
No, sir.
So our next topic is trickling filter. What is trickling filters? So trickling filters are artificial beds of crushed stones. So this is like a filter media or other porous media through which the settled sewage is allowed to percolate. Trickling filters are widely used for the biological treatment of waste. The liquid waste is applied intermittently over the top surface of the filter by means of a distributor. The filtered liquid is collected at the bottom through a filter box and under drainage system. So let's see a trickling filter. This is the trickling filter. So here these are the crushed stones. These are the crushed stones. Okay. So basically they are like this. Okay. And the water percolates through them like this. This is the sprinkler. These are the sprinklers. And through these sprinklers you distribute the sewage. Okay, you distribute the sewage over the filter media, and the filter and the sewage eventually infiltrates or percolates through the filter media, and finally the effluent is collected. Now while the sewage percolates through the media, the sewage is getting treated. How? I'll show you. If you look at this figure from the top, that means plan view, it will look like this. These are the sprinklers. Okay. Now what happens that, let's say, let's take one aggregate from here, one stone, this one. Okay, let's bring it here. So this is the sewage that is percolating through the pores of the filter media. This is the sewage. Now sewage contains what? BOD, organic matter. Am I right? Now this organic matter is a food of microorganisms. So as a result, the microorganisms will grow on the surface of the stone. So this is the layer of microorganisms. Why they are growing? Because they are getting food from here. Okay, BOD, organic matter. So they are oxidizing them. That means they are breaking them down and using them as a source of energy, and they are reproducing more bacteria. So there is a layer of bacteria here which actually acts as a cleaner or oxidizer, oxidizing agent, that in the presence of oxygen they can oxidize the organic matter. Clear?
Yes, sir.
This is
Sir.
the biological growth. So that has been explained here, organic removal. If you look at the figure here, this is the trickling filter. This is the trickling filter. Before we put the sewage into the trickling filter, we use a primary clarifier. That means this is the primary treatment. Primary treatment of the sewage. After the primary treatment, then we apply the sewage to the trickling filter. That means here. And then we have a final clarifier where we further treat the sewage. So this is the influent for this whole system. This is the influent and this is the effluent. Sometimes we recirculate some portion of the flow from here to there. Recirculation. Why? This is written here. Recirculation is the return of a portion of the treated or partly treated sewage to the treatment process. The main purpose of the recirculation is it provides a longer contact time in the filter and loads one reduced since the sewage is diluted due to recirculation. So what happens that this sewage is treated already by the trickling filter to some extent, right? Now you are again putting this here. That means you are increasing the treatment further. Clear?
Yes, sir.
That's one thing. Another thing is the seeding of the filter is done continuously with active organisms and enzymes. Now, this water already has bacteria in it. So you are recirculating this water. That means you are recirculating the bacteria and put it again here. You are putting the bacteria again. That means, you know, when you want to grow yogurt, make yogurt. Did you make yogurt ever? Yogurt. What you have to do? You have to put some yogurt initially. Why? Because this initial yogurt has some bacteria in this. These bacteria will get the food and they will increase in number. So to get a lot of bacteria, you need to start with some of the bacteria so that they can grow in number. Am I right?
Yes, sir.
So this is called seeding. So by recirculating, you are also seeding. Okay. Now, if you look at here, we have many formulas and equations and theory to design trickling filter. We have Eclairnier formula and other formulas. Anyway, so if you look at the trickling filter, this is the Li you are putting here, initial Li, influent. This will be changed because some portion is getting recirculated from here. So basically, there are three flows. One Li, one is LF, this, and the one is this. This is LE actually. This is LE, so this is also LE. This is LE, this is LI, this is LF. Clear? This is also LE. This is LE, this is LE. Everything is here LE because you're not mixing anything at this point. Is it clear, guys?
Yes, sir.
So here LF equals to Li plus R into LE divided by R plus 1. What is R here? R is the recirculation ratio. So R equals to recirculated flow. That means, let's say this is QR. this one, flow, discharge from here, QR, divided by the incoming sewage flow. That means QI. This is the QI. This is the QI. So QR divided by recirculated flow divided by incoming sewage flow. That means QI. Clear? Clear, guys?
Yes, sir.
Okay. So L E by Li equals to will be this 1 plus R 1 plus 2.5. D is the depth of the trickling filter and Q is the flow. So minus R. So QI, that means Q. QI is actually Q. Okay. So the removal efficiency also gets changed with the temperature, like K. This is the formula. We have another formula that's called NRC, National Research Council of USA. Okay. According to this formula, if you use multiple trickling filters, trickling filter 1, trickling filter 2, and this is the recirculation ratio R1 for trickling filter 1, this is the recirculation ratio R2 for trickling filter 2, then your efficiency E1 for the first trickling filter, this is E1, efficiency will be 100 divided by 1 plus 0.008 W1 divided by V1 F1, where W1 is the applied load, pounds BOD per day, pounds 5-day BOD per day, and V1 is the volume of the trickling filter. Okay, in acre feet, you have to be careful about the unit. Okay, this has to be in acre unit, acre feet. F1 is the recirculation factor. F1 is the recirculation factor, F1, which can be determined from this equation. You know R1. So if you know R1, you'll be able to calculate F1. Similarly, the efficiency for the trickling filter 2, E2, can be calculated from this equation. Clear? Is it clear, guys?
Yes, sir.
Yes, sir.
So in next class, we will start the examples based on the theory we have learned on trickling filter. So any question, guys?
No, sir.
Okay, then thank you very much. Have a good one and stay safe.